Now, in our last lesson, we did the DOL circuits, and those motors could be connected directly online. And now, today, I want us to start with how do we connect large motors. Now, it's usually not desirable to start large KVA-rated motors directly online due to various reasons. Now, in my other lessons, when I talk about large, it will not be referring to the size, it will be referring to the KVA rating in case I fail to mention it. And basically, there are two main reasons. One of it is that the KPLC, the power supply regulator, normally may give a requirement. The Power Supply Authority regulations, the large starting currents for large motors would cause a momentarily dip in the supply voltage. Remember, with motors, when it's stationary, when you are starting it, the currents may be 5 to 8 times large. And when that current flows in the distribution cables, it can cause a dip in the supply voltage, and that one could be harmful to other consumers. So that one is a major issue where we don't start large KVA-rated motors on the direct online method. So the KPL, the power supply people, will normally give some recommendations. Or if you're installing one, as I said earlier, consult them if you are new in their area. Now the other one is to ensure longer life for the motors. Now the large starting currents, which you said they're about 5 to 8 times of the rated current, would give the motor a shock. Now that sudden inrush of the current is what I'm referring to as a shock, i.e. sudden large currents in the windings every time the motor is started. Now, those large currents every time the motor is started, leading to a reduction in its length of service. Now, what affects those large currents when the shock comes in? It mainly affects the windings. The windings of the insulation, the winding insulation deteriorates faster with this kind of shocks. So basically, these are the two main regions, two main impediments we want to overcome when we are starting with the large motors. Now, the methods adopted for starting large motors, there are various methods. One is by reducing the starting voltage. If the starting voltage is small, the inrush currents will also be small, so none of this will be interfered with. And the other method is to reduce the starting currents. Basically, those are the two methods which are used. Now, one of the methods is what we call the Stator series resistance. In this one, we connect some resistance in series with our stator windings. Remember, we are still on the cage rotor induction motor. These are my terminals. We have got our star point there. The windings are connected in star connection. Then these resistors are connected in series with the stator windings. Then this resistance is gradually reduced. As you can see, the current will be flowing through there, then through this arm here, and down to the motor. So there'll be a drop here in the voltage across that region there, a voltage drop, same here, the same value around there. So here, there'll be a voltage drop across the resistor, and the balance will go to the windings of the motor. And then the value of this resistance is gradually reduced until we reach our, what we call the run position. At the run position, when it reaches the run position, this sliding knob here, the resistance will be out of the circuit, and then the full voltage will be across our windings. So series resistor with the windings. Now the key thing to remember is when we use the series resistor, it is important when we switch off the motor, these resistances should be brought back into the circuit. Otherwise, the next time we start, the whole voltage may come into the motor. So in the run position, R for run, once the motor starts, then when the motor stops, the sliding knob should come and include some resistance in our circuit so that the next time we are starting, the currents are, the voltage is reduced and then the indirect currents will be reduced. So that's for one method whereby we have stator series resistance. And of course, now we know Ohm's law, there will be some power loss in the resistances given by I squared R. So again, there's a limit to how large this motor is, as this loss here will be power wasted. So usually this one is normally used for what I would call small, large motors. Well, the word is my coinage. In the large motor series, there will be some which will be small, others will be big. So these losses, depending on the size of your motor, you should consider about the losses before you go for the method. Okay? Okay. Now, the other method we can use for reducing our starting voltage, we connect stator series reactance, we connect a reactance in series with our motor. Then once it starts, the inductance is gradually reduced until when it reaches the full running, the full rated current, the inductor will be minimized. Again, once the motor stops, we should make sure that the inductance is back in place before we restart the motor. So with the connections, you simply gradually reduce your inductance as the motor picks up speed until you reach your run position, and then the motor can run normally. Key thing to remember, after the motor stops, the inductance should be put back into the circuit. Now, this one can be said we used now the series resistance, we said it's for the small, large motors. This one you can say maybe it's for the large motors, because we know that in the inductor, no power loss in the inductance, no power losses in the inductance during the starting. So these are methods you can adopt. If you had a dual circuit, remember these connections here go to the dual circuit. You had a dual circuit, then maybe your company has brought in a bigger motor, then you can adopt either this method or that one. So basically those two, reducing the voltage, can be used. Now it's for you to simply judge whether to go for that one or this other one here, and then we can look at the other method which is available, which is referred to as the star delta starter. And this one here will reduce the starting current. Remember, we said there are two methods. You can either reduce the starting voltage or the starting current. So in the star delta, which is a kind of a more universally adopted method compared to the other two, reduces the starting current. So the star delta connection in this method here, normally the circuit will reduce the starting current to 1/√3 of the full load current, 1/1.732. It comes to about 0. Less than half, I think. So I've drawn the power circuits and the control circuits. Now, the power circuits is more or less universal, but we find that when it comes to the control circuits, normally you design it according to the components you have. As you can see here, my timer I've mounted on top of the main contactor is the one which is mechanically actuated. I said you can have a timer which is standalone, in which case that one will be connected somewhere here. And then the timer contact is the one which is used for the star. The normally closed contact, again the conventions, normally closed, normally open, normally closed. We have done that before. This will be the standalone timer. But here we have got one which is mechanically mounted on the main contactor. I think I showed you last time when we were dealing with the accessories. So in this case here, we first of all run the motor in star, where the current is reduced to that value, and then we change over to delta connection. Now, if you recall, our motor terminal circuits, we said you have to check on your motor how the connections are before you connect these circuits. So the one which I've drawn the circuit for follows the BS convention, whereby the stator windings are connected in such a manner. So these are my motor. The connections, we said you use a meter to know how the windings are connected. Now, in star connection, I will simply short these terminals here, and then this is for the star connection. When I do that one, it will mean my stator windings will be connected in a star connections like that one. And then when we want to go for the delta, if you recall last time, I said you simply make a connection between here and here, here and here, here and here. The beginning of one winding, the end of the other winding. The beginning of one winding, you connect it to the end of the other winding. The beginning of one winding, you connect it to the end of the other one. And then in the delta, the connection will be something like that. So you need to remember what we are changing over. Now in the delta, I said we connect top to bottom, top to bottom, top to bottom. In star, you simply short this one here. So if we briefly analyze our power circuit to see how we achieve that one, we can see that my star connection is when I want to connect the lower terminals, all of them together. Now if you view my circuits here, the lower terminals, which are these ones here, they have come to these terminals of the delta contactor, and then they are shifted over to the S contactor. And then when the S contactor peaks, this one will close. And when it closes, it will be tantamount to shorting these ones here. So all this will be connected together. I get my star connection. Okay? And then when you want delta connection, I said I connect top to the bottom, top to bottom, top to bottom. Now that I achieve with my delta contactor, and as you can see, this terminal here comes to the top here, when the circuit is connected, top here, and then the other end is connected to this terminal here. So when the data is connected, is akin to connecting top to the bottom one. For the middle one, this one comes down to that one. So the delta you connect the top side to the bottom, and similarly for the third one, top to the bottom. If these windings are differently, then the connections here will be slightly different. Okay? Then of course we have got our thermal overload, the main fuses, isolator. Now the key thing to remember is, if you look briefly at the circuit, we must ensure that the star and the delta should not be energized at the same time. Otherwise we'll be shorting the phases. So we need to interlock them. That when one is energized, the other one should be de-energized, and vice versa. So briefly, in most circuits, the power circuit will be simply mainly like that, with some slight, maybe some slight alterations. The key thing to remember also is that in case you want to connect a motor to star delta, these windings of this motor here should be able to withstand the full three-phase voltages. That means, as you can see here, between L1 and L2, we have got the 415. So not all motors can be connected to star delta. The windings you are having here should be able to withstand the 415 volts. Since when you connect to the delta, the whole of the voltage will be across one coil. You should be able to withstand that one. The other key thing is the star and the delta, we make sure they should not be energized at the same time. So now let's briefly look at our control circuit. Now these ones, again, the design is, they are different depending on how you design. Well, the design on this one was based on the components I'm having. What I have, it can be slightly different. Remember, the drawing will give you the principles of the connections. And remember, I told you in industry, there's more additions to the basics. There's more additions before the circuit is operational in industry. There are some other things we need to check. So in our control circuits here, from the live, we go through the control fuse. We go through the overload, which will be actuated by this relay here in case the motor tries to draw a higher current. Then the stop push button. From the stop push button, there are available some two paths. One will be through this path here to the main. When it becomes energized, there can be a path there when this one is on. And the other path, it goes to the start push button. And then right here, it is split into two. One goes through this connection through the star contactor, contacts open, star closed, down to our delta contactor. And then the other path is through the delta, normally closed, through the timer to the star contactor. Now, I've added here indicators. Sometimes in industry, you may be having so many motors, or when you are there, you want to know whether the motor is running in star or delta. So these ones here are indicators. Remember when we met first time, I gave you an assignment on symbols. So this is a symbol for an indicating lamp. So when the star is energized, that lamp will light. The delta is energized, that lamp will light. The main contactor is energized, that lamp will light. Of course, in industry, the story is slightly different. As you can see, this can light when this one is not energized. In case you have a break there, you can see our lamp will be lighting. So in industry, there is some slight modification. Actually, what we do is a contact of this one here is wired in series with this indicator lamp here. So you are sure when this one's lighting, actually this one is on. Some additional modifications in industry. Now, my contactors here are running at 240 volts from live to neutral. I said in the market, we have contactors which run on 415. So instead of going back to neutral, it will go to maybe, if this one's L1, it will go to L2 through a fuse. Now, of lately, I've seen some circuitry, mainly Chinese, and what they do is that these control circuits here they run it on 24 volts. That means here, these contactors here will be operating on 24 volts, but they can switch on our AC. So the design is entirely yours. What you have, you come up with a design. But the principles basically remain the same. So let's look at the control circuit, how it operates. Now, when you want to start your motor, this L1 usually will be tapped from maybe here. You switch on your isolator. This one's here, our main fuses. And the MDS, I've given their description here. Main contactor, delta, star, and timer. Sometimes they use Ks, K1, K2, K3. Other times they use the main for the delta, they use the delta symbol. For the S, they use the star symbol, timer, the J. So when you want to start your motor, you put in your isolator, you put it on. When you put it on, the feed is available up to the stop push button, up to this point here, and up to this point here. Then you push your start button. When you push your start button, this path here is available. When the start button is making, the feed will flow from the L through the stop, through now the starter, delta contact, normal not energized, the timer, the timing has not yet ended, and then your star contactor is energized. Normally in my design here, I want to make sure that the star connection is made, this connection is made before I connect my power supply. So the first contactor to pick will be my star contactor. Now once the star is energized, remember you are still pressing this one here, then this contact here will make. Now when this one makes, this one here will open. So actually my interlocking, to make sure that the star and the delta cannot be energized at the same time, I've used that contact and this one here for the interlocks. If one is energized, the other one cannot be energized. So now here, when the star has picked up, this contact here will make, and then this contact here will open. So no feed can ever get to the delta. Now when this one makes here, it provides a path for the main contactor to make. So after the star, the main contactor is energized, and I told you the main contactor is mechanically latched with my timer. So when the main is energized, the feed goes to our motor, and the motor starts running, and our timer also starts doing the timing. Now when the main contactor makes, this contact here will close. And when it closes, it provides us with a hold-on path when we release our start push button. Remember, I said the start push button is spring-loaded. Once you release it, now there will be a path for our holding of our control circuit through overload, stop push button, through now this main contactor which is making here. It holds on our main contactor to continue running. And then this other feed here, main is making, there's a feed through here, through this star which is now making, and then to continue connecting our star. So I have now the star, the main, and the timer working at the same time. Now after the preset time, this timer will operate, and then it will simply open this contact here. After the preset time, 5, 10, or 20 seconds, this contact here will open. Now when this one opens, there is no longer a feed for this one. And when there is no longer a feed for this one here, this contact here will close. And when it closes, my delta is energized. And when the delta contactor is energized, that one opens. And of course, this one has opened. This contact here is also open. So my circuit now will be getting my feed, control, fuse, overload, stop push button through this main contact here, which is still making, and then come to this point here to make my delta continue running and my main contactor on so that now my motor runs in delta connection, which is that one there. And then it runs. When you want to stop, you simply push in your stop push button. And that briefly explains the operation of our star delta connection. Now, in case you have a standalone timer, the one which I've shown in dotted here, that one means this one's not there. It simply means the contact of this one here will simply replace that one. Okay? And of course, depending on the designer, this circuit can be designed slightly different with some modifications. The stop push button they use in industry are slightly modified again, especially when you have got so many motors. Like when you're using these ones for the forward and the reverse, you have to make sure that when you're starting, the other one is not making. So the contacts of these ones here, the way it is designed is such that for a reverse connection, the starting of maybe the forward are involved with the reverse. But basically here, this one here gives you the principle of operation for our star delta connection. In star, the torque is less. When you connect to delta, the torque is more. Circuit analysis will give you the theory behind the star and delta connections. Now the key thing to remember, the timing we use here will normally be given by the manufacturer. When you buy the motor, the manufacturer will have a label. If you are connecting it to run from star to delta, then it needs to run so many seconds in star before you change over to delta. And that is the time you will set on your timer. So it runs in star. After the preset time, it changes over to the delta. Now this kind of arrangement sometimes is referred to as an automatic star delta starter. Now the automatic bit is only the changing from star to delta. In the earlier versions, that change used to be manual. Somebody will make these connections here manually, then he will listen to the running of the motor, he will know it has reached the preset speed, and then he manually takes it over back to he pushes it over to the delta. It used to be a manual connection. So it will depend on the ear of the operator of the machine. You connect it in star after the starting, and then you listen to the motor, you hear the sounds changing, and then you push it to the delta. That used to be manual. Now this our circuit here sometimes is referred to as automatic star delta starter. The automatic bit is only the changing over from star to delta. Sometimes if you get that timing correct, your motor might stall when it changes over to the delta. So get the manufacturer's setting for how long it should run in star and how long it should run before you change it over to the delta. So this kind of a method adopted for most motors, large motors, when you want to start them, the star delta starter. Remember, the contactors will determine the values of the currents for your motor. I think that should be okay. Await your comments. Briefly, in our next lesson, I'll look at other methods of starting the large motors. I'll give you drawings of which it's the auto transformer. That one will be reducing the voltage. And then after that, we can do some demonstrations of the connections. I think I showed you the components. So now we can maybe connect and see how we understand our circuitry.